All right, welcome back to part 3, where the goal is to make a static Linux executable that'll run just using the Linux kernel and make a full game. And if you remember in the first two parts, what we have here is if we go into our dump cycle folder, what we have is we have our, if we open up an editor, and we go to our main file. First episode, we implemented this little C runtime in assembly, and then you used it to create a hello world program. And then if we open another file here, in our second episode, we created this, we added to our makefile the ability to build an initial RAM file system and run our executable as the initial process in a QEMU virtual machine. So for example, if we go into our dump cycle into another terminal here and we do make test, it's going to boot a virtual machine that will run our hello world program. And there we can see hello from init right down there. Okay, so today what the objective is to actually draw pixels to the screen. And it's going to be a little bit of a process because, as I'll explain, the direct rendering manager verb is a bit of a beast of an API. It's not terrible, but it is there's a lot of steps. If you've ever worked with a graphics API, you know that most of them require a lot of steps. So just to set the goal here, oops, that was my bird hit the window there. Freaked me out. I thought there's a lot of snow on my roof right now, so I was worried that something catastrophic had gone wrong, but it looks like we're all right. But as I mentioned, so we're going to try to draw pixels to the screen today, and just as a little motivation, I have this little software rendered pattern that I made in Raylib a while ago to demonstrate something. And all it does is it's going to iterate, it makes a texture and renders that texture full screen. So it has a texture that's the width and height of the window, and it's going to iterate through the pixels from y equals 0 to y equals height minus 1, and from x equals 0 to x equals width minus 1. And it's going to set the red component to be the x pixel position mod 255 or and with OXFF, and so truncating off the low 8 bytes. And the same for the green, it's going to set the y, the low 8 bytes of the y coordinate, and then the blue is going to be the x and y added together, and then take the low bytes of that. So if you want to see what that looks like, it's going to be this scaling pattern. And also, the motion is it's giving an offset that's being incremented every time this frame is drawn. So we're going to do the same thing using just the direct rendering manager and dumb pixel buffers, which are what they're called in the direct rendering manager parlance, which means pixel buffers that are rendered by the CPU, just writing values into memory, not using any GPU functionality, hardware functionality. Okay, so if we jump into my handy-dandy GIMP notepad here, we're going to talk a little bit about how the direct rendering manager functions. And the way the direct rendering manager works is we're going to have a device. In our case, we're going to assume it's dev DRI. This is where all the direct rendering manager card files are. And we're going to assume card 0. And that will be our video card for the renderer we're going to use with the direct rendering manager. And each card is going to have a set of card resources. So the card resources is going to be, in our case, they're going to be a set of connectors, an array of connectors, an array of encoders, an array of CRTCs, which is a legacy acronym for cathode ray tube controller, but in this case it just means anything that's going from a plane of pixel data and converting that to the format that the connector accepts. For example, in old days with CRTCs, they would actually have an array going across, so they have to do timing and such for that ray rendering. But it's a little bit different nowadays with like HDMI ports or whatever other display adapter you have. And then we're going to have frame buffers also as part of our card resources, FBs. And so these together are called the card resources. And the way we display pixels to the screen is we're going to take a frame buffer frame buffer, which is going to be a 2D array of RGB RGB. I'll just we'll talk about that in a second. But RGB pixels in memory, and that's going to go to a CRTC, and that's going to go to an encoder, and that's going to go to a connector. And this is our HDMI port or laptop screen or etc. And how we're going to construct this with the Direct Rendering Manager is we're actually going to go in reverse order. So we're going to open our card 0 device. We're going to grab its card resources by making a system call. Then we're going to select a connector. Usually there will be an active, if there might be an active connector already. We'll select a connector that has a mode of connected, which means it's ready to display pixels. Then we're going to see if that connector already has an encoder and a CRTC set up, and if so, we'll use that. Otherwise, we'll cycle through the encoders and see which ones are compatible with our connector. Same thing, we're going to go through and find a CRTC that's compatible with our encoder and connector. And then finally, we're going to create a frame buffer to hold our pixel data and write pixels there. So that's going to be the process. We're going to open this dev/dri/card0 device, get the card resources, find a connector, find an encoder and CRTC that are all compatible, create a frame buffer, and then just by writing into memory, we're going to be able to draw pixels to the screen. There's a lot of steps that are going to be involved here because we're going to need, for example, on our current system, when we run this in a init process, remember our initial file system doesn't have this dev file system set up. So we're going to have to set that up. That's going to be very, very simple. I'll show you how. And then we're going to have to open this. So we'll need to implement the open system call. We haven't even implemented open yet. We're also going to need memory mapping, mmap, to map the frame buffer will be a part of memory that's going to be associated with this card 0 file descriptor. We'll have to map that with an mmap system call. We're also going to need mmap to get a block of memory to allocate some memory from during runtime, and we'll have to implement a little memory arena to do some allocation. There's a lot of steps involved today. And in addition, I didn't mention that the system calls for all the stuff we're doing with the Direct Rendering Manager, there's no bespoke system call for that. It's all done through the Swiss Army knife system called ioctl, or input-output control. And we'll have to implement that, and we'll look at the Linux kernel API for that. So, to get started, the first thing we need to do is we need to get our hands on this dev/dri/card0 file, and we need to open it. So, if we are back in our host system here, we can see that if I do ls on dev/dri, we have some files here, and in particular, we have this card0. I believe this render D128 is for hardware-supported video rendering and encoding, but don't quote me on that. I think that's what it is. But card0 is the device we have here, and that's what we're going to use to render. And it's going to be the same thing on our QEMU virtual machine. Eventually, maybe I'll show how you can we could just iterate through the card devices and pick one that's working and connected, and has support for dumb frame buffers. But on most systems, this card0 is going to be what you want, so we're just going to do that from the start. And in particular, it's the one that we'll want for our QEMU virtual machine. So, first thing to do is let's just implement open and open this dev/dri device. But it doesn't exist, so we'll implement open, and then I'll talk about that. Okay. So we need open, and we can go back to our browser and look at the system call table here. Open is system call 2. It takes a const char pointer for the file name, takes flags, and it takes a mode. And we're not going to care about the mode because we're not going to try to create. Mode is for like creating or appending to files. We're just going to open it in normal mode. And we do care about flags because this controls whether the file is open for reading, writing, etc. So let's implement the system call, and then we can talk about the values for that. So sys open is system call 2. It's going to return an int, which is our file descriptor. Open const char pointer fname int flags, and then int mode. And all it's going to do is return syscall sys open, and we'll cast our fname pointer as a u64. Fname flags mode, and then 3 zeros. Okay. Now, how do we find what those flags are? There's a few different ways we can go about this, but the easiest way is, remember in that first episode, we built that sysroot for muscle_libc. Well, in that sysroot, in the include directory, we have the fcontrol header here, and fcontrol has the flags for open, because that's where open is defined in the C standard library. And the C standard library open is going to be a thin wrapper around the open system call, so the flags are actually going to be the same. If we wanted to, we could jump into the muscle_libc implementation, which we will later do to see how mmap is implemented. But it really is just going to be a thin wrapper around the open syscall. So if we open up fcontrol here, and we scroll down, to be even more correct, we could take a look at what we're searching for here. So if we do man2 open, we look at the manual page for open, and we search for this. We can see it describes the open system call function definition. If we search for flags, the argument flags must include one of the following access modes: O read only, O write only, or O read write. And so we want to search for these within our header file here. So I think I was just past it there. I had them right here. O read only is 0, O write only is 1, and O read write is 2. So we can define those in our own little enum here. Enum open flags, O read only is 0, O write only is 1, and O read write is 2. So now we have defined the flags we need for open. So if that file existed, we could at the start here, I'll leave our hello world for now, but we won't be using it once we actually get to drawing pixels on the screen. I could do open, int, I'll call this card fd. It's going to equal open of dev dri card 0. And we're going to be opening this with read and write. So O read write. And mode is going to be 0 because we don't need a particular special mode. We're not creating or appending to a file. Okay. So if we, one thing we did last time was we had the ability to open this in a debugger. So we can compile this and see what cardfd is. So if we make debug, what were our, it's just saying our cardfd is unused. Then let's close out of here. Let's do dump cycle. Then if you remember, we can open a debugger. I'm going to add to the make file to make this all automatic in just a second. But if you remember from last time, what we have to do is we do gdb. We load our dump cycle executable with gdb. Then we do target remote 1234. That is the ::1234 TCP v6 address, IPv6 address over TCP that the QEMU is hosting a GDB server on. And then we connect, and then we would do hbreak main to break at the main function for our init process here. And we continue. Then we get here, and if we step down, we can print what the cardfd is. It's -2 because, as I mentioned, our initial file system doesn't have this dev directory loaded. And luckily for us, we don't need anything special like udev provides, which is the one of the ways that it used to be traditionally managed on, and it still is often traditionally managed on a full Linux distribution. It's just a daemon that'll manage the dev/dev directory and create all the nodes for all the devices. The Linux kernel provides a way to automatically detect what devices are connected and set up the /dev directory, and that is called the dev temp file system. And so all we need to do that is we need to mount the dev temp file system at /dev. So we just need to implement the mount syscall. So if we go to our table here and we look for mount, that is syscall 165. And it's going to take a device name, a directory name, a type, flags, and data. And so the device name is going to be the device you're mounting. For example, if you mount /dev/HDA, you have like a physical hard drive device. That would be the device name. The directory name is the directory which the device is being mounted. The file system is being mounted. The type is the file system type. And then flags and data are generally I think at least data is file system specific. We could do a little man mount here, man to mount, and look at mount flags. Okay, mount flags are not file system specific, but the void data is going to be a file specific parameter that you can pass to it. We won't care about all that. The dev temp file system, in fact, if we look at this, the dev temp file system, in fact, only requires a directory name and the dev temp file system type. Because it's not mounting a particular device, it's mounting the file system itself kind of defines the device. It's mounting the dev file system. Cool. So let's implement this. So if we go back up to sys, we're going to have sys mount 165. Then if we go to exit, right after here we can implement our mount system call. So we'll return an int, which will be our error code, int mount, and it will take a const char pointer device name, a const char pointer directory name, a const char pointer type, int flags, and then a void pointer data. And then to implement that, it's going to do syscall of sys mount. We'll cast all our pointers as u64, dev name, u64 dar name, u64 type, flags, and then u64 data, and then a 0. And we auto-formatted that. Okay, so hopefully we should have our mount system call correctly specified here. And now what we're going to do is before we try to open this card, we're going to have a call to mount. We could pass in just the empty string for, in fact, we could probably pass in null if we wanted to, but empty string works just fine. It's going to be ignored anyway. /dev is where we are going to be mounting the file system. And dev temp fs is the file system type. We're going to do 0 and 0. So all we're specifying is that we should mount the dev temp file system at /dev, and dev does not care. We don't really care about these flags, and we don't care. Dev temp file system does not take any additional data. Now the special thing about this is with 0 flags, the mount call will fail if this dev folder exists and already has something mounted on it. So if you are on a system, for example, if we want our executable to run as not just an init process, then this will work fine. This mount call will just fail if you already have your dev directory set up correctly. So let's try this again. And so just to make things a little bit faster, let's go into our makefile. And I'm going to have the debug, the make debug command actually start a debugger that is attached and have it break at main. So we don't have to do all those steps in between. And so what I'm going to do is I'm going to write ampersand here to run this in a separate, to fork this and run this in a separate child process. And then I'm going to start GDB. I'm going to do -q so we don't print that preamble. And I'm going to do dumb cycle. And then GDB allows you to specify commands to be executed right at the start, so with an EX flag. I'm going to execute target remote 1234. I'm going to execute hbreak main, and I'm going to execute continue. So now I'm going to close this and everything. Now, if we save this, and we make debug, it gets us into a debugger at main right automatically. So we don't have to go through all those extra steps. Now we can step mount, and we can print card FD. Oop, it's still -2. Let's see here. Yeah, every time I practice this, this has happened. Oop. Let's return. Make debug. You know what? Let's see. Over here, I do. Okay. Yeah. We're going to add this VGA virtual IO here just to make sure that we're all running the same DRM driver. And look behind the curtain. I'm actually testing this on a kernel that's not exactly the same as the one we built in the first episode. I'm testing it on a very minimally compiled kernel that only has DRM drivers for the virtual IO driver. And so when I was running this other way, apparently it wasn't even providing a card 0 because the DRM wasn't working. If you had built with make def config, I believe this should have worked, but I'm testing on this very minimally compiled kernel. We'll show at the end, I'll show later on when I pull out my laptop that we can run this pixel thing on any computer as long as you have your kernel is sufficiently configured for the device you're running on. Let's for testing, let's use this VGA virtual IO so we make sure that if you're following along at home, you're going to get the exact same driver as me. But if you had followed the instructions in my video, which I did not, okay, I guess behind the scenes, because just for testing, I wanted to make sure it worked on the minimally compiled kernel impossible, and I didn't really want to go through explaining the full kernel configuration. But we're going to run with VGA virtual IO, and now, as you can see, it is finding this dev/DRI card 0. So the mount was always working. It's just that our drivers weren't configured. The kernel I was running did not have drivers for the video card it was trying to use. But so we have our card 0 open. So we've got to the point where we can start requesting card resources. And here's where things get interesting. So we are going to implement the ioctl system call, IO control. And let's take a look at that in the man page here. So we're gonna exit this. It is working. We have verified that we've gotten to here, and we have a file descriptor for our video card. So let's look at the system call. So man to ioctl IO control. So it's going to take a file descriptor and an operation, and then I think technically afterwards it always is going to be a void pointer to additional data. I just spilled water on myself. And so the thing we care, file descriptor is self-explanatory. The void pointer that is going to be the third parameter that's not even listed here in the API, but it is always the third parameter, is going to be somewhat self-explanatory. It's going to be just data that is provided with IO control. The op is the interesting part here. So if we search for op, an ioctl op has encoded in it whether the argument is an in parameter, an out parameter, the size of the argument, argp in bytes. So argp is going to that void pointer. That's the third parameter that I mentioned. And it also defines what subsystem it is using and basically the operation that is being performed. And if we go down farther, actually, there is more specific information about what is encoded. Later, some more information was built into the number. One has 2 direction bits, 0, 0, none, 0, 1, write, 1, 0, read, so this is 1, 2, and 3, and 1, 1, 3, read, write. Followed by 14 size bits. Those are going to be the size of that struct. If you're not following along, we'll implement it so you'll get another crack at it and see exactly how it's going. Followed by an 8-bit type. So this is going to be collecting different operations in terms of drivers. So in particular, the 8-bit type for DRM is the character literal lowercase d, the ASCII for that. And then an 8-bit serial number, which is going to be a particular operation for this device. So when we specify the type, the ASCII value for lowercase d, that is specifying the DRM driver, and then the DRM will have a series of different operations you can perform on it, and those are going to be encoded in this 8-bit serial number. And most of those are going to be read-write requests, and so the size byte is then just going to be the size of the struct that we're passing forward and back between the kernel and ourselves. So really it's just encoding a bunch of stuff into one 32-bit number. Somewhat historical reasons why this is done this way, but it's not too tricky to get your head around. So let's implement this. So if we go back to our syscall table and let's do ioctl. That is syscall number, make sure we're in the right table, yep. That is syscall number 16. It's going to take a file descriptor, a unsigned command, and then a unsigned long arg, which is generally going to be interpreted as a pointer. So I'm gonna type this as void pointer. So in our system call, we're going to go to sys ioctl is 16. After open, we will implement int ioctl. It's just going to return an error code, I believe, if it fails. Although some rare ioctl calls do actually use the return value, but I don't think ours is going to. And it's going to take a int file descriptor, an unsigned, I guess I'll do u32 to follow our naming convention, our u32, which is going to be the operation, and then a void pointer data. And it will return syscall sys ioctl. File descriptor, op, and then u64 cast data, and then 3 zeros. Okay. Now the trick is going to be, what do we pass in here? So we're going to implement another function that is going to pack an operation. Now if you look inside the kernel headers, which is how I initially figured out how to do this, I didn't realize it was specified also in the man page. You will find that there's a series of macros that are generally used to pack headers. But since I'm trying to avoid the preprocessor as much as I can in this project, we're going to do a function that is just going to pack the operation at runtime. And we don't really care too much about the performance of these calls. It's not going to impact us massively. We're doing software engineering. We're not going huge on performance here. So it's going to be u32 ioctl op, I'm going to call it. And it is going to take, if you remember, it is going to take a direction, a size, a type, and a serial number. So we're going to do u32 dar, u32 size, u32 type, and then u32 number. And all this is going to do is going to return and these are actually specified in reverse order in terms of low to high. So the serial bit is the lower one. It's not quite clear here, but if you look at those macros I specified in the kernel headers, it will become clear there. So the low bit is going to be num. So we're going to turn num and oxff. So we're going to take off the first byte of num just to make sure that we don't get any excess bits if we messed up and we passed num something too big here for num. And then we're going to take type and oxff, the first byte of type, and then we are going to also, let's see, we're going to bit shift this up by 8. So the next 8 bytes are going to be type. Then we'll OR that with size, and so we're going to need 14 bytes. So that's oxff is 8 bytes. Add another f, that's 12 bytes. Then we need two more bits. Sorry, 12 bits. Now we need 2 more bits, which is going to be 3 for 1, 1, right? So 3 f is 14 bits. The first 14 bits, and then we're going to up 16. We're going to shift that over by 16 because the first 16 bits were already taken by num and type here. And this is the next 14. And then finally, we're going to OR this with the first 2 bits of direction, and those are going to be the last 2 bits. So that's going to be dir and ox3. And we're going to shift that over 30, right? 16 plus 14 is 30, but also we know that is a 32-bit number and the last 2 bits of the 2 direction bits, so those are going to be shifted. Okay, so that's how my auto formatted this. A little bit unfortunate there with the trailing parentheses, but it's fine. And yes, so we can now pack IO control operations. We just need to know what to put in there. And the first thing we know is it mentions this right here. The 2 direction bits are 0, 0, none, 0, 1, write, 1, 0 or 2, read, and 1, 1 or 3, read, write. So we can pack those in here. So we'll do enum ioctl dir, ioctl dir read only is going to be 1, ioctl dir write only is going to be 2, and ioctl dir read write is going to be 3. I believe these are different than they're specified in the headers, but we'll use our own names. It's fine. Then size is going to be something that's going to be dependent on the API, what struct we're passing for this, the size of the struct we're passing in this void pointer data here. And type, as I mentioned, we'll need to find out from the API as well, type and num. So we need to know what the kernel API is for the direct rendering manager. The easiest way to do this is to get the kernel headers for the kernel we're using. So if we go to our root directory here and we go into our Linux source code, if you remembered, to build the Linux kernel, we ran make o equals home demo build Linux, and then we just ran this with usually j nproc to build our kernel. Now, if we want to install the Linux headers for this kernel, you need to add. You can run the make command with headers install. I think I already must have ran this in demo. So if we go to go to build Linux, yeah. So I already ran this, and I think this has some. I've been resetting my directory when I practice, yeah, and it has a git ignore in here, so it wasn't resetting this according to the git repository. But if we go into user, we're going to include, then we have the headers for the Linux kernel that we're using for our virtual machine and test. And these are going to be pretty universal for x86-64 Linux. It's not particular to our configuration here. So these are the headers for the Linux kernel for x86-64 on whatever version we're on, 6.12.67. So the Linux directory will have most of the basic Linux headers, but we have this DRM directory here that we're going to jump into that will be the headers for the direct rendering manager subsystem. So in DRM, we're going to edit drm.h and drm-mode.h. And so when I explain the direct rendering manager here, I should have mentioned this, I realize now. This usage of the direct rendering manager is called kernel mode setting. So when you're usually interacting with the direct rendering manager as a user space process, you're usually interacting with it via a host program like the Wayland compositor or an X server that is providing you some part of the DRM to interact with for your for just to do stuff on the GPU. This part where we're actually managing connectors, encoders, and how pixels are getting drawn to a device, that is called kernel mode setting. And mode setting is just setting the display mode of a device. And so our game is going to be doing the mode setting. It's not going to be interacting with another device, another window manager there that's doing that for us, which is unusual, but our goal is learning about the Linux kernel, not necessarily making a practical game here. We are making a practical game, but it's designed to handle everything from scratch and just run on the Linux kernel, which is not a normal game that you'd distribute to somebody. Okay, so if we open these two files, so in drm.h, we're going to see IOCT. Let's go drm ioctl get resources. Oh, is that in mode? Get resources. Get resources. Ah, here we go. drm ioctl mode get resources. That's what I was getting wrong. So this is defined as a drm io read write. So that's another macro. So let's look for that. drm io read write read. So that is specifying io write read drm ioctl base, then the number and the type. So the number and the type is what is being passed in, and then it's we know we know that part. This is the macro for packing an ioctl request I specified earlier. And here's, as I mentioned, the drm ioctl base. That is that type parameter to that was mentioned in the man page, and also how we specified here is going to be D. So we will add that to our code here. Enum ioctl type. I'm going to do drm. I'll just do ioctl type drm is going to be D. But I won't name it exactly the same thing. And then the size is going to be the size of this particular struct. So we'll actually have to copy some definitions of struct in from this API. But these nums are what we're going to need as well. So we'll do enum drm ioctl mode get resources is going to be, so if we go back to get resources, the number, which is that first parameter that was passed into this drm io read write macro, is oxa0. So oxa0. And then the struct it's passing in, which will determine the size parameter and what we have to pass a pointer to in for that void pointer data argument, right, down here, is going to be drm mode card resources. drm mode card resources. So that is actually going to be in the drm mode header file. And here we have a simple struct, drm mode card resources. So let's grab this and go back into, let me see, I think I have to, sorry, I think I did it right, but let's yank that and then let's paste it down here. So we're gonna do all our DRM stuff down here now. So here's our DRM mode card resources. I'm going to change these to match our type definitions. The kernel has its own. And in particular, I believe if we look in here, let's see, where does it explain what those are? Maybe it doesn't explain in here. Anyway, I happen to know that FBIDs are U32s. So this is not a U64, it's actually a U32 pointer. So we're just going to be type correct. CRTC IDs are U32s, so we have a U32 pointer. In fact, all these IDs are U32s, so we're going to have a pointer. So instead of, when they said U64, what they really meant is it's a 64-bit word, which is actually representing a pointer to an array of U32s. And then these counts are the lengths of the arrays. Otherwise, this definition is fine. And now we can make our first IO control system call. So let's get rid of our hello world here. or we can leave it. Yeah, let's get rid of it. And so what we need to do is we need to define one of these. You know what? I'm going to have this open in parallel here. We need to define one of these card resources structs. Struct DRM mode card resources. And I'll call this res. We'll just initialize that to all 0. And let's try making an ioctl system call. So we're not going to care about the error of mount here, but we will care about it for here now, for our ioctl. ioctl. So ioctl, the first is going to be the file descriptor, which in our case is our card FD, the file descriptor for our video card. Then we are going to pass in a packed operation. So ioctl op. Let's go over here. ioctl op. And that's going to take a direction. In our case, it's going to be ioctl dar read write. It's going to be bidirectional. We are going to take a size, which is going to be size of res, the struct we're going to be passing a pointer to. It's going to take a type, which is going to be DRM, ioctl type DRM. And then it's going to take a number, which is the number of the DRM system call particular operation we're performing, which is going to be DRM ioctl mode get resources. Okay, and then finally we're going to be passing a pointer to those resources. So if we let my auto formatter do it, it's a little bit more readable now. So we're passing in the card FD. The operation is a read-write operation with an argument of size of res. It is for the DRM subsystem, and it's the get resources request. And we're passing a pointer to res. So let's run this in a debugger and see if we implemented everything correctly. So if we do make debug, let's see, we have our card FD correctly. We have our res, so if we print res, it's all 0s right now. Now if we step and we print error, there was no error, and what if we print res now? It has filled out some information. So we have a count of CRTCs. There is one CRTC for this video card. We have a count of connectors. There's one connector. We have a count of encoders. There's one encoder. And we have a min width, max width, min height, max height for this device. So in general, this is a very simple driver. We're using the virtual I/O driver, right? So it's just providing one CRT, one connector, one encoder, and so on. But we're going to write our code to work with any number of encoders, connectors, CRTCs. And I'll run it on my little laptop in the same method we did at the end of last episode, just to show it'll work. But in general, and we have 0 frame buffers. So what we're going to have to do, as I mentioned, is we're going to have to grab this connector, encoder, CRTC, and then we're going to have to create a frame buffer to write pixels in. And we're going to have to do that all together. Now, if there could be a lot of these, depending on your video card. And so one thing I'm going to introduce here, we're going to need memmap later on anyway. And one thing I'm going to introduce here is we're going to do some dynamic memory allocation. So if we had libc available, we could use malloc and free and so on, right? But since we're not, we're writing our own C runtime, and I don't want to implement something as complicated as malloc and free. What I'm going to implement is I'm going to implement the mmap system call, which will allow us to ask the operating system for pages of memory. And then I'm going to implement a simple memory arena, which is just an allocator where you can allocate it's essentially a pointer to a start of a section of memory and a pointer to the end of a section of memory. And then as you allocate, it simply reserves as much space as you need for your allocation and keeps going. And eventually, if you hit the end, that's catastrophic. But we're going to allocate enough that we'll never hit the end unless we do something wrong. And the only way you can free it is by setting everything all the way back to 0. So you essentially allocate and you don't free unless it's the last thing that was allocated, which means you can move it back up, or you can free it all at once. Might be a little complicated if you've never seen it before, but it's incredibly simple, so you'll get it right away. Let's quit out of here. Let's close our virtual machine. So the first thing we need to implement is the memmap system call. So if we go to our table and we look at memmap, it's got all question marks. I'm not entirely sure why that is. I think it might be just the way that that Google parsed out this information from the kernel headers. But little to fear, we have a full implementation of a libc that we compiled in the first video, so we can just jump into that. So the thing I'm going to do is I'm going to go to muscle, and I'm going to source. I'm going to go to mman, memory management. I'm going to open mmap.c just to see how they implement mmap. So their mmap function is going to take a start pointer, a len size, protection int, flags, a file descriptor, and then an offset. And then it's going to do a little bit of stuff with the flags first, but then essentially just pass all of these to mmap, right? So it's going to pass them to sysmmap with start, len, prop, flags. So really this is just a thin wrapper around a system call. So we can do that too. So if we remember, mmap is system call number 9. So we can go back up here. Sysmmap 9. Just above ioctl, just after open, we can do mmap. It's going to return a pointer, so void pointer, mmap. And we can verify that in the code here. See, it's casting the return value as a void pointer. And this syscall ret macro, all this is doing is it's checking if the return value from the system call is in that negative 495 to -1 range, which indicates an error, if you remember that from the first video. And if that is true, then it is returning, it'll set the return value to 0 and actually set the global error no value to whatever that error was. In our case, we're going to just return a null pointer if we get an error, and I'll show how to check that. But it is casting, if it's a valid memory mapping, if there wasn't an error, it's just casting a return value as a void pointer. So that's what we will do. And it's going to take a void pointer start, a i64 len, and then what else? Then it's going to take a int prot, int flags, and then an int file descriptor, and an i64 offset. And we are going to return as a void pointer for now syscall of sysmmap cast u64 r start. Then we're len, prot, flags, file descriptor, offset. We actually used all 6 of the parameters to our system call. And as I mentioned, we actually don't want to do this. So what we're going to do is we want to make sure that there's no error first. We're going to do our u64 ret is going to be equal to syscall, and let's save this to get. It's just a little. Let's close this and make it full screen so we can see everything for now. And then we're going to check whether this return value is in the bad range. So we're going to do if ret is greater than negative 4096 ul. So this is negative 4096 treated as an unsigned long, so it's going to be at the very top of the unsigned integer range. Then we're going to we'll return 0. The literal 0 when treated as a void pointer is a null pointer. I'm not going to implement a null macro just because I said I'm not doing macros. But all the null resolves to is the 0 literal in C anyway. So we're going to use return 0 for a null pointer. Otherwise, we're going to return void pointer ret. So we're not going to bother parsing out that particular error number here because really I don't expect mmap to fail. And if it fails, I've never experienced mmap failing in these experiments. So if we're being nice, we could extract the error no and store that somewhere. But in particular, we might be in a debugger so we can inspect that ourselves, what the ret value is. Or in general, I've never known mmap to fail for these simple purposes we are using it for. Okay, so now we have an mmap system call. And to have a chunk of memory to use, we can mmap it, but then we need, so let's do that. Let's map, and I'm going to define a const i64, I'll call this arena size and I'm going to do 4096, which I'm going to assume is the page size. Eventually, maybe, I know it's the page size for this virtual machine we're running out in the kernel I configured. Some kernels do have a larger page size, like 16 kilobytes, but I'm going to assume 4 kilobytes is our page size, 4096. Like I said, we could parse the page size out of that auxiliary vector in our runtime, if you remember from the first video, but I'm just going to assume this for now. So I'm going to, the mmap requires you to map in multiples of the page size. So I'm going to map 4096 times 2000, which is 4 kilobytes times 2000, which is going to be around 8 megabytes. So that's going to be our arena size. And so let's memory map that. So we're going to have a void pointer mem. It's going to equal to mmap. The start parameter for mmap is just a suggested initial address, virtual address, if you want to request a particular address, which can be useful for more complicated allocators and such. But we're not going to care about that, so we're going to pass null. Let's look at mmap here. The next is the length of the allocation, so that's going to be our arena size. It's how much memory we're going to try to allocate. Then there's this prot and flags parameters. So as before, we can go into the sysroot and grab out the flags and stuff we need. But to know what flags we're looking for, we should probably read the manual page. So let's do man to mmap, and let's search for prot. The prot argument describes the desired memory protection of the mapping. It is either prot none or a bitwise OR of one or more of the following. So we can do prot exec, read, write, or none. In our case, we will so we'll need to look at what these are. Prot read we can search for to find these. We won't need executable memory to map that, so we're going to look for prot read and prot write. And then let's go back up to the start here. Flags. So let's look for flags. The flags argument determines whether updates to the mapping are visible to other processes mapped in the same region. This behavior is determined by exactly one of the following values in flags. Map shared validate, map private. We're going to map shared. That is just generally the default. We're not going to be doing much multiprocess stuff in this, if any, I believe, in this project. Entirely single-threaded. But we'll just map shared because that's the easy default to go to. And I believe, where is it also? In addition, 0 more of the following values can be ORed in flags. And the one we're going to care about is map anonymous. The mapping is not backed by any file. So we're just going to request memory, general virtual memory from the operating system. We're not going to be mapping any file into memory. At some point, when we do that map for our frame buffer, we are going to be mapping backed by a file descriptor, and that file descriptor will be our video card file descriptor. But for this initial arena that we're grabbing, we are just mapping anonymous memory. So we need to look for map anon and prot read and prot write. So let's open up sys/mman, which I just happen to know is the we can, if we go back to it, we can see that it is included in the man file. It specifies that the sys/mman.h is the header file for mmap. So if we open up sys/mman and we search for, oh, here we have right here. So map anonymous is ox20, so hex 20, which I believe is 32. So let's go back up to our mmap implementation here. We're going to have an enum mmap prot, and that's going to be prot enum mmap flags. So this is going to be map anonymous. It's going to be ox20. And we need to look for map shared as well. Map shared is ox10. Map shared is hex 10. Oh, 01, right? Yeah, sorry. And then here, we need to search for prot read and prot write. So prot read is 1 and prot write is 2. So prot read is 1 and prot write is 2. Okay, so now we can fill out these. So the prot, we're going to do prot read ORed with prot write, right? We want readable and writable memory. And then we want our flags to be map shared ORed with map anonymous. We want shared memory, which is just the standard memory we'll be mapping. It won't be, if we did do multiple processes things, then they would have access to it as well. And anonymous, we're not backed by a file descriptor. The file descriptor flag is the next one. We're running short on screen space here, but the next is a file descriptor. I believe it is traditional to pass -1 there. We could look at the man page, and that's what it's going to say. And the offset, we're not mapping a file descriptor, so the offset into the file doesn't matter. So if we save, oops, it auto-formatted it for us. So let's try running this in the debugger and see if we get some virtual memory. Make debug. We got some valid virtual memory. Okay, so we were able to map an 8 megabyte chunk of virtual memory from the operating system. Now I want to implement a tiny little arena allocator that will allow us to allocate little bits, allocate arrays or space for structs from this chunk that we get from the operating system. I'm just going to shamelessly copy this fantastic, this little implementation from Chris Rellin's blog, nullprogram.com. Fantastic blog on all things C. And this is a very tiny arena allocator implementation that he has that we will just steal for our purposes. His code is all very leniently licensed. I believe it's even all public domain, but don't quote me on this particular thing. But in general, he does do that. But I'm not saying anything about the license of the code that we're writing here. Let's go to the bottom here. We'll do it above the DRM stuff. Really, I should probably, my decision to not use header files is a little bit cumbersome for the layout of the code. Really, we should have like the implementations and the definitions separated out a bit. But I've decided to do it this way, so we're going to stick with it for now. So here's our implementation. Arena is a struct. We're going to change it to follow the coding style I've been following here, which is we won't type def our structs. We'll have them in the struct namespace. And then we're going to have a struct arena. Instead of pointer diff t, we're going to take this nice portable code and make it only work with x86-64 because we're not using the standard C headers. So we'll search for pointer diff t. We'll replace that with i64, and then uint pointer t will just be a u64. So pointer diff t is a signed integer size that can store the difference between any two pointers. In our case, i64, we're in a 64-bit address space. And then a uint pointer t is the unsigned integer that's the same size as a pointer. And so in our case, that's u64. And we are not going to take the alignment. We're going to assume the alignment is 16. So alignment is when you allocate memory, what is that address divisible by? So for example, the address 16 is divisible by 16. The address 8 is not divisible by 16. Address like 5. And the reason for this is that historically certain, and still currently, certain assembly instructions will only work with memory that is aligned. For example, if you have a 32-bit struct in memory that is aligned at 5, that's going to be an odd position in memory. And some things care about alignment. In general, I believe malloc will always align things to 16 bytes, which is the maximum required alignment of any type in Linux x86-64. And so we're going to do the same as malloc, and we're going to align everything to 16 bytes, even though I believe all the types we're going to be using today will only require 8-byte alignment. But so we're going to get rid of that align parameter, and wherever align is, we're going to replace it with 16. And then the final thing is we have a few libc functions used here. So abort, if we run out of memory, it is going to abort. We can just replace this with exit of 1 for now. So if we run out of memory, we're just going to kill the program. Really, though, what I should probably do is let's implement a panic function. So I'm going to do a void panic const char pointer message. What I'm going to do is going to write to standard error. I'm going to write message and strlen a message. So when we panic, just for development, I want to be able to expect what's going on. So instead of killing everything, I'm just going to hang in an infinite loop. A little bit strange, but because we're testing our thing as an init process in this virtual machine, the best way to just panic is to write to the standard error and then hang in an infinite loop, in my opinion, for now. We probably won't keep this forever, but I'm going to panic. Instead of exiting 1, I'm going to panic with out of memory. And the final thing here is memset. So what this is doing, it is setting all the bytes that we just allocated to 0, because when you, I believe when you mmap from the operating system, they're default set to 0. But if an arena was allocated and used for something and then freed and then reused, it could be non-zero. So it's just setting it all to 0, which will be useful for us later on. But we haven't implemented memset, and this is the only place I'm going to need memset, so I'm not going to implement it. So what I'm going to do is I'm just going to have a for loop, i64, I equals 0, I less than count times size, I plus plus, p bracket I equals 0. We'll just return p. So all we're going to do is we're going to iterate through all the bytes that we just allocated and set them equal to 0. So I probably should have gone through this implementation. If you've never seen an arena allocator implementation, what this first line is doing is it's calculating. So our arena, as I mentioned, is a pointer to a start of a memory chunk and a pointer to the end. And as we allocate, it's moving the beginning up. So for example, if we need a certain amount of space, it's taking that space and moving the beginning up. And so what this padding is saying is our current start begin aligned to 16 bytes? If not, it has to move down to start at 16-byte aligned address. So it's just ensuring that that this pointer is 16-byte aligned. So the padding is how much we have to add to get to 16-byte alignment. Then the available is the difference between the actual space available between that 16-byte aligned start and the end. And then it is checking whether it can actually allocate that, and this is just to avoid overflow. If we have a really high, accidentally passed in a really high size and count, this avoids some overflow. And then it's saying that the pointer that the start of our new allocation is going to be the beginning pointer plus whatever padding was required to get it to 16-byte alignment. Then we are reserving that space, the padding plus all the size we just aligned, to be the new beginning of our arena. So we're getting rid of all that, marking it as used. And then I'm going through and I'm zeroing out all that space we just allocated. So this alloc is a way of allocating from our arena. So now in our home here, we will have a way of allocating memory. And the way we'll do that is we'll have a struct arena, and I'll just call it arena. And we will set begin is going to equal to our memory, and end is going to be equal to memory plus arena size. Auto-formatted like that. So we're setting up our arena to be that chunk of memory, virtual memory we just allocated from the operating system. Now we have a way of allocating memory. As I said, this is going to be a process. So the next thing we need to do is we're going to make this we're going to get our resources, and like I said, if you remember, let's run a debugger just to we need to you know what, we'll call this a char pointer. If we're going to iterate through the bytes, we need to have it have a size type, and we'll just treat it as bytes, char pointer. Here we go. So what I care about is if we remember what our resource struct here looks like. Oh, we haven't made our ioctl call. We got from the operating system that there is one CRTC, one connector, and so on. There might be more depending on your video card. The virtual video card just has these one. But what this first call is doing is really just asking the operating system how many there are. Then we need to allocate space for these arrays, and we need to make a second call giving it a pointer for passing it in a valid pointer for each of these arrays, and the operating system will fill out those arrays with the actual identifiers, so that all the frame buffer IDs, CRTC IDs, connector IDs, encoder IDs, and so on. So that's what we needed our alloc structure for, our allocation for. So to see that, we are going to, below DRM mode card res, we're going to implement a function, and we're going to return DRM mode card res pointer. And we'll call this DRM mode get resources. And for parameter, it is going to take a int file descriptor and a struct arena pointer arena. And so what it's going to do is we're going to grab in here we're going to do the same thing, but instead of just creating on the stack, we're going to actually allocate it from our arena. So at the start, we're going to, in case anything fails, we're going to do this currently in a temporary arena. So what you can do with arenas, we can do a struct temp arena is equal to arena. So we dereference the current arena, which is saving the state of the arena. We do all this stuff in the temp arena, and if our operations fail, we can just reset everything back and return the arena. Now, really, this doesn't matter. This is just good practice for if you were implementing this. If we were implementing our own version of libdrm. In our case, if getting the resources fails, our game can't work, so we're just going to bail out anyway. But I'm just going to follow along this way just because it's good practice. So we're going to start with a temp arena. Then we will allocate our struct DRM mode card res pointer res is going to equal alloc temp arena. So we're allocating from the temp arena size of res, and we're allocating 1. We're not allocating an array. Let's fill the screen here. So we're allocating 1 DRM mode card res struct from our arena. Then we're going to make a call to make our ioctl call. And now, since it's not in the stack, we actually have to dereference here, and we don't have to take a reference here. Then what we're going to do is we are going to save the contents of this this first call and make a second call. And the reason for this will become clear in just a second. So we're going to do a struct DRM mode card res temp last res. So we're going to save the result of this first call. We're going to call last res is going to equal dereference res. We'll also just check if error equal if error is not equal to 0, then I will do panic failed to get resources. And you know what? I'll just return 0 from here. I'll just return a null pointer, and we can deal with that afterwards. Okay. So we make our first ioctl get resources, which will get the counts of all those arrays, right? Then what we need to do is we need to allocate space for these arrays. So what we need to do is we need to allocate space for each array. So we need to set res. Let's remember what the DRM mode card res. Okay, so we're going to get these counts filled in, right? Count FBs, count CRTCs, count connectors, count encoders. But we don't have arrays to store the actual values in yet. So what we need to do is we need to allocate them. So res FB ID pointer is going to be equal to alloc temp arena. It's going to be size of res dereference res going FB ID pointer, and then res colon count FBs. Let's do make, see what the errors are. Oh, I need to, oops. Struct arena. Okay. Okay. So we're allocating space for this, and we can do the same thing again. We can just replace FB with CRTC. Then we can do the same thing with you know what? Yeah, they are all the same. Okay. We can do the same thing with replacing FB with connector. We can place connector with encoder. Okay, so we should have allocated an array of the correct size for each of the types of IDs we're getting. And now we can make another call to ioctl. This time, we won't have to create error again. With those arrays now are not, those pointers are not null now, so the operating system should fill out the arrays. Now there's one thing that could happen here if we want to be absolutely correct, and that's what we're going to have to handle here, is what if between the first ioctl call and the second ioctl call those numbers changed, such that there's no longer enough space to fit the number of encoders. Somehow another connector popped up, which has its own set of encoders. Then there's more, those counts increased, but we only allocated space for the old counts. So the completely correct way to do this is to actually have this whole part be in a loop here. So we're going to have a do while loop. So we're going to do this. That's why we saved that last res. While we're going to do this loop while last res dot count FBs is less than res count FBs. If the first call had fewer frame buffers than the second call, or we're going to grab this. I'm going to make 4 of these, because that's how many there could be wrong. Okay. Now, frame buffers, it could be FB, it could be CRTCs. It could be encoders. Oops. FB encoders. Or it could be FB, it could be connectors, right? Okay, format of that. So if any of these increased since the first IOC control call to the second one, then we need to redo the loop. And we are resetting our temp arena at the start each time. And actually what we need to do is these both need to be declared outside the loop, my bad. But the temp arena needs to be set at the start of each loop. Okay, so at the start of each loop, we're resetting our memory allocation. We're asking the operating system for the counts of all these stuff. We're allocating arrays for them to be written in. We're making another call, and as long as everything went okay, then we're done. But if any of those counts increased, then we won't have enough space, and the operating system wouldn't have written them all in there. And so we're going to need to go around again. And so at the end, if everything worked correctly, what we need to do is we need to set that actual arena to be the temp arena. So we're dereferencing arena going to equal temp arena. To say all those allocations that we made to the temp arena, those are actually allocations we want to make, and we'll return res. So just to go over what we want here again one more time, we allocated space for a card resources from our arena. We declared this temp last resource stack variable and a temp arena. Then in the loop, we are setting the temp arena to be equal to the current state of the arena. We're making an ioctl system call to get accounts. We're allocating an array of each type of ID according to those counts. Then we're asking the operating system to fill in those arrays, and then we're done. Unless those counts change such that they won't fit anymore, and then we have to do the whole process over again. But otherwise, we're done. So we commit the temp arena to be a real arena, and then we're returning the resources pointer. Let's run this in a debugger and see if it works. So if we do make, okay, we have one thing here. Temp arena undeclared. Where is this? 163. Oh. Ah. So this just needs to happen at the same point here. I have a feeling that there's a better way I could have done this, but we'll just do this right now. That makes sense. We want to allocate our arena after our temp arena is set up. Good C compiler card FD. Oh, we're calling this just FD here. Let's change this to be card FE. We should probably have this, we'll have a care pointer mem. Unused variable arena. Oh yeah, we have to make a call to this. So we'll have our struct drm mode card res pointer res is going to equal drm mode get res of card fd and a reference to arena. Actually have to call that function that we made. C compiler warnings are helping us here. And then it's just warning that our resource variable is unused, but we haven't used it yet. So we can run this into debugger and see what it gets. So make debug. Let's print arena just to see what we have here. So it is showing that we have basically 8 kilobytes mapped here between our virtual address spaces. And we are going to print our card FD just to make sure it's right. Yeah, 3. That looks good. Let's step inside drm mode get resources here. So let's do layout source just so we can have a little bit clearer picture of what's going on. So we're inside our loop. We've set up our temp arena. We've allocated one of those drm mode card resources structs from our arena. Then we're making our first ioctl system call. There were no errors, so let's print last res. And just as before, it's having those counts filled in. But now what we're doing is we're going along and we're allocating space for each of these arrays, right? So if we iterate through this, and before we make our ioctl system call, let's print res. It is going to have a pointer now filled in for each of those arrays to be stored at. And if we print, you know what? I see something we did wrong here already. Some of those counts might be 0. So for our alloc function, we need to do if size equals 0 or count equals 0. Let's return a null pointer. Return 0. So we'll return a null pointer if we try to allocate a 0 amount of size, which I see we're not doing right now, which is fine, but we should probably do that. Everything will still work, I believe. So if we do it next and we print error, there is no errors. Now if we print our actual resources, it should be the same, but if we print resources bracket FB connector ID pointer, we get the 0th element of that. It filled in an ID, and I know this to be the correct ID, so it's actually working. And if we print res, we see that the counters did not change because our virtual video card driver is not going to change those counters from 1. So it verified that those counts did not change such that the lengths were invalid. Now it's committing the arena memory, res, and we have our card resources. And we can look at them. So if we print res colon CRTC ID pointer bracket 0, we can see there's an ID for that too. And if we print res encoder ID pointer bracket 0, you can see we get an ID for that. So the IDs are 36, 37, 38 for our associated objects that are resources for our card. So there we are. We have resources. Okay, I had to take a little break there to rest my voice and have some lunch, but we're back. So we have we've got our resources. Let's quit out of here and close our emulator. And we go down here. We have our card file descriptor open. We've mapped some memory so we can allocate, and then we're able to grab our card resources. So if we go to back to our little picture here, what we have to do next is we have to get a connector object. We have the connector ID, we have our list of connector IDs, encoders, and CRTCs. We actually have to select a connector, select an encoder, and a CRTC, and then we'll go through the process of creating a dumb frame buffer that we can write pixels into just in our virtual memory. So let's do that. So the first step is to get a connector. So if we go back to our DRM headers from our Linux headers, if you remember, these are the headers from the Linux kernel API. The next request we're going to look for is get connector. Get connector? Yeah, it's all one. So this is going to be the serial number for this request is A7, so we can add that right here. So if we go to, I forget where it was, A0 was our first one. Yeah, so it's our DRM ioctl enum. We're going to do DRM ioctl mode get connector, and that's OXA7. Okay, and if we go down to get, yeah, our next thing is going to be get connector. So, not here. Oh, no, it's right here. Okay. So we need to grab the struct DRM mode get connector, which I believe will be in DRM mode. DRM mode get connector. So this one has a little comment that describes the API a little bit, but let's grab the get connector here real quick. Oh, it has lots of comments. Fantastic. Oh, I think I need to just forget that I'm copying between different editors here, so we're gonna. Okay. Once again, we're going to have to change these to match our let's get rid of the tabs here as well. Okay. So we have it formatted correctly. Okay, so DRM mode get connector is going to have so this is going to be a pointer to a, so we're going to edit this to make the types correct again. So encoder's pointer is going to be a pointer to an object of U32 array of object IDs. So we're going to replace this with a U32 pointer type. Props is going to be also a pointer to object IDs, so U32 pointer. Same with prop values. A U64 array. Okay. And then modes is going to be a pointer to a struct DRM mode info. Okay, so we should grab that from in here too. So DRM mode info. Mode info, I believe. DRM. Of course. DRM mode info. Here we are. We'll need this as well. Of course, I forgot to do this faster. Okay. We're going to have the types replaced. Now we just need to grab this DRM display mode len, which I believe will be in here. Oh, maybe it's in here. 32. Okay. Don't need this anywhere else. Just 32. Okay. We have our DRM mode info thing, and then we can change this to a struct DRM mode info pointer. So we have the correct types. These are the counts for those arrays. Connector ID. These are the IDs for the current encoder and connector that are hooked up to this connector. Connector type, and then stuff about the connection. Subpixel type. Okay, cool. So how we actually do this is we are going to let's read struct DRM mode get connector. User space can perform a get connector ioctl to retrieve information about the connector. User space is expected to retrieve encoders, modes, and properties by performing this ioctl at least twice. The first time to retrieve the number of elements, the second time to retrieve the elements themselves. So it's exactly the same way as we got our card resources. To retrieve the number of elements, set count props, count encoders to 0, set count modes to 1, and modes pointer to a temporary struct DRM mode info element. Okay. And then to retrieve the elements, allocate arrays for encoders. Okay, so we can do this. And again, this is what we were handling before. Performing the ioctl only twice may be racy. The number of elements may have changed. So we're going to actually copy our implementation of get resources, and we'll just do the same thing for get encoder, slightly modified. Okay. So we're going to need to do the similar thing here. Actually, we need to copy one more thing, which is the no, we're good. Okay. So start out, we're going to be replacing DRM mode card res with DRM mode get connector. We're going to DRM mode get connector, and we are going to also take a connector ID, I believe. U32 connector ID. because I believe yeah, the connector ID is the connector where we have to set the connector ID in that struct, which is the connector we're actually requesting information for. We'll call this, let's replace res con, and otherwise we should be okay. So the only thing we need to do here is before we make the ioctl call, we need to set con connector ID equal to connector ID. We also need, what did it say up here? We need to set count modes to 1 and modes pointer to a temporary struct drm mode info. Okay, so we need to we'll create a temporary struct drm mode info. So set con count modes 1 and con what's it called? Modes pointer is going to be a reference to mode info. Okay, so we've set things up as requested. Then we're going to make our first call, but instead of get resources, we're going to make a get connector ioctl call, right? And then we're going to set last con equal to con. And now here we're going to change things. Our arrays are count modes, count props, and count encoders. Okay, so we're going to set and what are the we have encoders pointer and count encoders. So that's going to be the same. We have modes pointer and count modes. So modes pointer and count modes. Oh, and it's even though it's actually encoder IDs, it's encoders pointer. And then here we are going to have instead of FBID, we're going to have, what is it called? Props pointer. Props pointer, count props, and then prop values. What is it? Prop values. Prop values pointer, and this is also going to use count props. Okay, then we're going to make another call, this time with get connector. I probably need to change all these names to modes. No, we did it right. Should be correct. And then, here's where we need to change. So we need to change count encoders. That's fine. We need count FBs. It's going to be props. And this is going to be modes. And then this last one is going to be goner. And if all is well here, we should be following the API. So we are doing the same idea where we're setting up a temporary arena. We're allocating space for our connector, our get connector struct. We're setting up the initial properties, which we didn't have to do for get resources because it was just dependent on the file descriptor. We're setting the connector ID we're requesting, and we're doing modes, count modes equals 1, reference to a temporary mode, as requested by the API. We're making the initial call to get those counts. Then we're allocating under all the arrays that are required, and then we're making a second call, and then we're last checking to make sure that those counts didn't change as a race condition. And if not, we're going to commit the arena and return a pointer to all that memory. So let's give this a go. The thing is, what we're going to have to do is we're going to have to go through all of the now let's look at the struct. So what are we looking for? We have an array of connectors in our card resources, right? So if we drm mode card res, right? We have an array of connector IDs. we're going to have to go through these, and we're going to find a connector ID that has a certain property that we're looking for. So DRM mode get connector. DRM mode connector. Status of the connector. Okay, yeah, this is what we're looking for. This is U32 connection, the status of the connector. This says see enum DRM connector status. Unfortunately, and I know this from experience, DRM mode connector status. What is it called? DRM connector status. Not in here. It's not in DRM. Unfortunately, this is not exposed in the public API. We're going to have to go into the Linux source code to take a look at this. So in our other terminal here, we're going to go into our Linux source code, and it's going to be in include DRM. And if we do, it's going to be in DRM correct connector, DRM connector.h. So DRM connector status. So there's an enum here that we're looking at. So connector status equals 1. The connector is definitely connected to a sync device and can be enabled. This is what we're looking for. So what we are going to do is we are going to define an enum DRM mode connector status. And what is this? It's connector status disconnected. So mode status connected is 1. Okay, so what we're going to do is we're going to iterate over all those connector IDs. We're going to call this get connector struct here, and then we're going to look at the connector the get connector struct that was returned and see if that connector is connected. Once we found one that is connected, we're going to use that one. We're not going to. There's some strategies where you could grab all the connectors that are connected. We're going to grab the first connector that is connected that we can display pixels with. So we're going to have a for loop here. For U32 I equals 0, I less than res count connectors I plus plus. U32 con ID is going to be res connector ID pointer. Is that what it is? Let's look here. Connector IDs pointer. ID pointer? Yeah, that's what it is. Okay, connector ID pointer, bracket I. So we're going to grab the ith connector ID. Then we're going to have a struct DRM mode we probably want a temporary arena here too. So we'll have a struct arena temp arena equals arena DRM mode connector DRM mode get connector, right? Con is going to equal, oh, this is a pointer, DRM mode get connector of our card FD, our connector ID, and a reference to our temp arena. Okay. So if con equals 0, if our connector failed to be retrieved for some other reason, we'll continue. Or if con colon, what is it called? The DRM mode connector, get connector. Okay, what is this? We were looking at the connection property. Connection is not equal to DRM mode, what did I call it? Connected. Let's copy this. So if it's not connected, then we also want to continue. Or there's one more thing here. if it doesn't have any modes, which is also a possibility. So if count modes is equal to 0, or con count modes is 0, then we continue. Otherwise, we are going to set arena equal to temp arena and break. And actually what we want to do is we want to have this variable persist. So we are going to declare this out here. We'll have it equal to null to start. And then we will just set it each loop. And then afterwards, we need to test if we actually found a connector, because right here we need to set we'll set it equal to null, just to indicate that we weren't able to find it. So if con is equal to 0, if we couldn't find a connector, then we are going to panic. Failed to find connector. Okay, so let's try running this in the debugger. Let's just try making this. I'm not going to need the Linux source code anymore. I just needed to find this DRM connector status enum. So we're going to go back into our dump cycle folder here, and we will try making connector ID pointer. Let's see, 372. Oh, modes pointer. Coders pointer prop value. Okay. Hopefully that was the only typo. Let's try and make. Okay, make debug. Let's see. So if we jump down to here, so let's see. What's our con ID? Should be that 37, right? Yep. So if we step in here, we're gonna walk through what we're doing. So we're allocating. Let's do layout source, just so we're see what we're doing. So we're taking our let's print our connector. We can see that we have our connector ID set up, our count modes equal to 1, and we have our modes pointer equal to this stack, this mode mode info struct on the stack. That should be correct. So if we do this and we print error, there's no error. So we save the last con. We jump down here. We're allocating, making our second. Do we have an error? No error. And this should all be valid. Oop. Let's see. What's the last one? What's on here? Ooh, what was count modes? 0. It's going to work. Let's print con. Print last con. Looks like it should be okay. Okay. Interesting. We should do the erase there. I'm not quite sure why. Okay, and it looks like we did not panic. And we are good. Let's try this one more time. Kernel Mode connector. Let's print con. Print last con. Now, I was confused about this. I think I guess this. I feel like I haven't done this in the past. What's this? Yeah, so we get the mode types count correct when we don't do that set count modes equal to 1 thing. So I'm kind of confused. I'm just going to keep doing it this way, even though I never read that header before, because it seems like otherwise we just have to do the whole thing twice. So I'm going to get rid of this. Maybe that's only if you want to look at the first mode. I'm not sure. In any case, I think we're going to do it this way. Cool. So we are able to iterate through and find a connector. Next step, we have to find an encoder and a CRTC. So there are two options. Our connector, if we look at our get connector struct, it could have a connector ID and an encoder ID already set up. In which case, we can look at that encoder to see if it has a CRTC already set up, which it usually will if there's an encoder already set up. Otherwise, if the encoder ID is 0, then we have to go and look through encoders and find a compatible one. So let's look at get encoder. DRM. Let's go back to DRM and look for get encoder. So it is its code is A6. So let's add that. So get connector. We're going to add get encoder. And the struct is DRM mode get encoder. So let's go over here, DRM mode get encoder. Encoder. Okay, here we are. We will put this right here. Oop, forget. Okay. Change the types to match. Okay. And this one has no arrays, so it's going to be a lot more simple. So we're going to have a struct DRM mode get encoder pointer DRM mode get encoder. Once again, we're going to take an int card FD. We're going to take a U32 encoder ID. We're going to take a struct arena pointer arena just to match all the other calls, even though we technically don't need it as much this time. Then we will look at get encoder. It doesn't have a nice comment explaining, but it's fairly self-explanatory. What we're going to do is we're going to say struct DRM mode get encoder is going to equal pointer encoder. I'll just call it enc. It's going to equal alloc. We'll make a temp arena. Arena temp arena is going to equal arena, dereference arena. Temp arena size of dereference enc. Cool. And count is 1. Then we have it formatted. Then what we need to do is we need to pass this to an ioctl call. Let's grab one of these just so we don't have to rewrite everything. Let's grab this whole chunk here. Okay. Okay, and error. So the only thing that's going to change here is we're going to do get encoder instead. Encoder. And we're going to replace con with enc. And as I mentioned, we're not going to have to make this call twice because there's no arrays that we need to allocate here. And the only thing we have to change here is we need to set our enc encoder ID equal encoder ID. We have to tell the kernel which encoder ID we're looking for. Otherwise, we're going to set arena equal temp arena, and we're going to return enc. So exactly the same, except it's less complicated because we don't have to do that whole get the counts, allocate the arrays, make sure that the counts didn't change. Okay. So we are going to do the same thing for CRTC. So let's go back to here, get CRTC. So that is A1, and the struct is DRM mode CRTC. So we're going to go get encoder. Yep, 1. So I messed this up here. Okay, now we are going to grab this struct, drm mode crtc. Here we are. Again. Okay. Once again, we're going to rename the types. Okay. And then we can copy this because it's going to be very, very similar. Encoder, crtc. Let's grab inc. Let's grab encoder, crtc. And mode is just going to be mode crtc, not get crtc. Then the last thing we need to do is rename our variable from inc to inc. We'll say crtc. Okay, so we're going to do the exact same thing, except we're setting the crtc ID, not the encoder ID. We're using this drm mode crtc struct. And this part here, this is a U32 pointer, set connectors pointer, and that's for setting connectors. So that is, I believe, for the set crtc syscall, not the get crtc call. Which we will take a look at later. So we should be all good. And it should be noted here, all throughout we've been taking advantage of the fact that alloc allocates everything as 0, which is a little bit tricky in C, because technically we're setting all the bytes to 0, and we're taking advantage of the fact that I shouldn't even bring this up. We're taking advantage of the fact that the null pointer is literally 0 bytes, the 0 pointer on x86-64 Linux. But if we were doing more platform independency, that wouldn't be necessarily the way to go. We should probably actually set it to the literal 0. Never mind that. Okay. We should be all right here. So we have get encoder and get crtc all set up. And as I mentioned, these pointers are actually not going to be arrays that we're going to get from the kernel. They're actually an in parameter that we're going to pass to the kernel for the set crtc call, which we will do later. Okay. That is how we will attach those frame buffers that we create. If we look at this picture here, we're going to have to create the frame buffers ourselves, and when we attach those to the crtc, we're going to have to use the set crtc situation. Okay, so we have a connector. We got this far. So we're going to have a struct drm mode crtc pointer crtc. We're going to start it with as 0. The first case, if you remember, is if connector encoder ID is not equal 0. So if there is an encoder already set up for this connector, then we are going to do struct temp arena, struct arena temp arena equal arena, say the temp arena. We're going to do struct drm mode get encoder. Inc is going to be drm mode get encoder of card fd con encoder ID, and then a reference to temp arena. Okay, we're going to get the encoder. Then if encoder, if we look at what this struct is, let's do parallel here. DRM mode get encoder. This is going to have a CRTC ID. So if encoder CRTC ID is not 0, is equal to, we'll say if it is equal to 0, we are going to, no, if it's not equal to 0, perfect, then we're going to grab that too. So struct, so we're going to set CRTC is going to be equal to DRM mode get CRTC of card FD, encoder CRTC ID, and then reference to temp arena once again. And then if CRTC is not equal to 0, so if we have a valid CRTC here, then we are going to set arena equal to temp arena. Okay, so we're creating a temporary arena just in case things fail. We're grabbing an encoder, the encoder get encoder struct corresponding to the encoder ID that is currently set for our connector. If that connector encoder has a CRTC set up, then we are getting the CRTC corresponding to that CRTC ID. If that succeeded, then we have a CRTC in hand that is already set up for our connector. Now, otherwise, CRTC is still 0. So if CRTC is equal to 0, then so this is the case where if our encoder did not have an encoder already, if our connector did not have an encoder already set up for it, we have to iterate through all the encoders and find a compatible one. So let's look at yeah, so this is the array we need to go through, not our DRM mode resources array, but just the encoders that are compatible with our current connector. So we're going to do a similar thing to what we did up here, just we have to loop over all the encoder IDs and try it for each one. So we're going to do for U32 I equals 0, we'll call this inc index equals 0, inc index less than connector count encoders and inc index plus plus. Okay, so we're iterating. Let's get rid of this for a second. We're iterating through all the encoders in our connector. So we're going to say U32 inc ID is going to be equal to calling encoders pointer bracket inc index. So we're grabbing the ID. What happened here? Corresponding to that that index. Now we are going to set up. So now we're going to do this. So we'll have a temporary arena for this encoder. We're going to get an encoder. But it's not going to correspond to concurrent encoder ID. It's going to be our inc ID we're trying here. Okay. Then we're going to do this same thing. We're going to iterate over all the CRTC IDs and find one that is compatible. Because if we look, let's go to mode CRTC. This is going to have or is it encoder get encoder possible CRTCs. Okay, yeah. So the CRTCs, possible CRTCs. Okay, yeah. So what this is going to be is apparently there's maximum of 32 CRTCs, and that is the index in in that DRM mode card resources. So the CRTCs array can be only up to 32, and so we're going to iterate over that, and the index of the CRTC ID corresponds to a bit in that possible CRTC's mask. Okay, so for U32 CRTC ID IDX equals 0, CRTC IDX less than resources CRTC ID pointer CRTC IDX plus plus. Okay, so we're iterating. We'll get rid of this for a second. Okay, we're iterating over all the CRTCs in our resources. If get CRTC. No, it's in the connector, right? Get encoder. Sorry, it's in the encoder. Yeah, possible CRTCs. Okay. So if CRTC IDX and so if what's gonna encoder inc possible CRTCs. This is the bit mask. The bit mask. We're gonna have to and that with CRTC 1 left shift CRTC index and if this is all not equal to 0, so if this is equal to 0, we'll continue. So we're going to take one. We're going to look at the CRTC indexed bit in the possible CRTCs and see if you and it and it's 0, that means that bit is 0, so that means it's not a possible CRTC. And we're going to continue. Otherwise, we're going to do struct. We're going to set CRTC. Remember, we have this global CRTC, this already defined CRTC pointer that we're trying to find. We're trying to find a valid CRTC. We're going to set this equal to DRM mode get CRTC of card FD. Oh, we're going to have to grab the CRTC index. U32 CRTC index ID is going to be equal to res CRTC. Oops. This should have been count CRTCs. CRTCs IDs pointer bracket CRTC index. So we're grabbing the ith ID out of the CRTC index ID out of the CRTC ID array. So CRTC ID and then a reference to temp arena. Then, if CRTC is not equal to 0, then we can set arena equal to temp arena, and we will break. And here once again, if CRTC is not equal to 0, we can break. I'm not sure whether it's clear to do that down there or down there, but in either case, we are good. Let's do it down here because this is the scope in which the temp arena was declared, so it makes more sense. So finally, if the CRTC is still 0, that means all those things failed. Then we will panic, failed to find CRTC. Okay, let's go over all this one more last time. Okay, so the first step. We have found a connector. We now need to find a CRTC and a corresponding encoder. Okay. So, the CRTC, we start with as null. If the connector already has an encoder ID attached to it, we check that. So we grab the get encoder struct corresponding to that encoder ID. If that encoder has a CRTC attached, which it should, then we get the CRTC struct according to that CRTC ID, and if that is valid, then we're solid. We set our arena equal to temp arena. Otherwise, CRTC is still null. So if CRTC is null, that means either this first step failed or there was no encoder already attached, in which case we iterate through all the encoders that are in that connector's encoders array. So we go through all from 0 up to count encoders. We grab the corresponding encoder ID out of the encoder's pointer, so that out of that array. Then we go through the process up above that we did for the first encoder once again. So we grab the encoder, the get encoder struct corresponding to that encoder ID. Then I guess we could check if that encoder already has an ID. But it's simple enough. I think the general idea is that if this step fails, then this encoder won't have a CRTC already attached to it, so we won't check that. So what we do is we iterate through all the CRTCs for our resource for our card, and we bit mask the index bit in the possible CRTCs for that encoder, and we see if that is a possible CRTC for this encoder. If not, we continue. If so, then we grab the corresponding ID, get the CRTC struct, and if it's not null, then we are solid. We break out, we save the temp arena to be the actual arena memory because this iteration worked, and we are good. And if we still couldn't find a CRTC after all that, then we panic. So let's see, can we make this? Oh yeah, we changed that. So get CRTC. Or was it get connector, right? What line was this? I'm a dummy. 335. Yeah, it was get connector. Okay. We ended up not doing that option. Okay, so we're gonna make debug. Okay, let's step through. We're going to find a connector. We found a connector. Let's print our connector. It does not have an encoder ID, so we're going to skip this step. Then we're going to go in here. I set up a temp arena. We're going to grab the encoder ID. Let's print the encoder ID. So this is 38. We only have one encoder, remember, for our simple array. So we're going to grab the encoder struct corresponding to that. Let's print our encoder. It's encoder type 5. Possible CRTC is 1. Possible clone is 1. Remember, only have one CRTC, and that CRTC is compatible with the one encoder, thankfully. So we're going to start iterating through. We're going to check possible CRTCs with one left shift over the CRTC index, which is one left shift 0 for us. So that was correct. It is compatible. We're going to get the CRTC ID. And our CRTC ID, I believe, was 38, right? Or 36. 38 was the encoder ID. 37 was the connector ID. For some reason, they're all swapped around there. CRTC. Okay, I got a little bit confused, but everything is working as expected. So if we break on DRM mode get CRTC, Anyway, the fact that all that stuff is 0 is to be expected because the CRTC was not set up yet, so it doesn't have a mode and registers, but the connector is what has the mode. So once we make our frame buffer in accordance with the connector and all, and we call set CRTC with our new frame buffer, then the CRTC will have its mode and stuff set. So everything being 0 is as expected. So next step, we have a CRTC. We need to handle this frame buffer. And what we're going to be doing is we're going to be making a dumb buffer. So if we look in here, we're looking for create dumb. Kernel mode setting dumb buffers provide a very primitive way to allocate buffer objects suitable for scan out and map it for software rendering. Exactly what we want to do. Scan out is frame buffer scanning out to a CRTC to the connector to the screen. And software rendering is we're going to go through each pixel and set it in software on the CPU, not using any GPU APIs. Not suitable for hardware accelerated video decoding. Dumb buffers are suitable to set on. Okay. Create user space is expected to create a kernel setting dumb buffer via this ioctl, then add it as a KMS frame buffer via add FB and map it via ioctl mode map dumb. So we're going to have to create a dumb buffer, add it as a frame buffer, so it becomes one of those resources that our card has, and then we're going to map it with map dumb, and then finally after map dumb we are going to make a mmap call to actually get access to that that dumb buffer memory in a virtual address. So we need create dumb, map dumb, and add FB. Get CRTC. Okay. So DRM ioctl mode create dumb is oxb2. DRM ioctl mode map dumb is oxb3. DRM ioctl add FB we want add FB1. I'll talk a little bit about that in a second. Add FB, let's just add FB, is OXAE. I think that should go there. And that's all we need. Okay. So we need a few structs, right? So for add FB, we need struct DRM mode FB command. So let's grab that one. DRM mode FB command. So at the top here, we're going to create these new. So a dumb buffer is going to consist of a frame buffer and a mapped set of stuff in memory. So I'm going to create a struct that will handle all this stuff for us. But let's copy this first. As usual. Okay. Okay. Now let's go back to here and let's create dumb. DRM mode create dumb. Mode create dumb. We'll grab this thing here. And DRM mode map dumb. We'll also need this. Okay. And for these, we will also get rid of okay. Cool. So we have all the structs that we need, and we have all the serial numbers for the frame buffer commands, the ioctls we're going to need. Yeah. So let's just add stuff as we'll just add stuff as we go. So I'm going to create our own struct dumb buffer. At the very least, we're going to need a U32 FB ID. We're going to need a U32 pointer mem, and we're going to need an I64, which is going to a U60. We'll call it U64, which is size. So we're going to need the ID of the frame buffer object resource. We're going to need a pointer to the memory, and we're going to need a size. And I know that we're also going to need a U32 width, a U32 height, and a U32 stride, which I will explain as we get to them. Oops. And this should be here. So, okay. So, we are going to create a new function, struct dumb buffer pointer, DRM mode create dumb. I'll just call it create dumb buffer, actually. And we're going to take in a int card fd and what else do we need? We need width and height. And I believe that is all. And a what's it called? And a struct arena pointer arena, I believe. Okay. Struct temp struct arena temp arena, as usual, is going to equal arena. Okay. So we need to create a dumb buffer, map the dumb buffer, add the frame buffer object with the frame DRM mode FB command, and then call mmap to get the actual memory. So let's do it one at a time. So struct DRM mode create dumb is going to equal create, we'll call crec, create request, is going to equal, let's look at what this struct needs. So create dumb, we can take a look at create dumb. Buffer height in pixels, buffer width in pixels, bits per pixel, flags must be 0, handle, buffer object handle. That will be returned to us from the kernel. Pitch, number of bytes between 2 consecutive lines, and size of the whole buffer in bytes. So user fills in height, width, bits per pixel, and flags. If the IOC control succeeds, the kernel fills in handle, pitch, and size. So we need to fill in height, width, bits per pixel, and then flags must be 0. Okay, so dot width is going to equal width, the width that was passed in per our function. Dot height is going to equal height. Height that was passed into our function. We'll read those off of the connector's mode. Dot BPP is going to be 32. We're going to have RGB plus 8 bytes extra for our flags, for our pixels, and then if we leave everything else blank, they'll all be set to 0, which is what we want. Okay. And the kernel will fill in the rest. So we're going to make an IO control. So let's grab this and go back down. And we're going to make another IO control here. Except instead of CRTC, we're going to do crec, and it's going to be size of crec, and then this is going to be a reference to our crec. This crec is not a pointer. We're going to do ioctl mode create dum. Okay, so this should work to create dum, and if error, we're going to return 0. The next thing we need to do is map dum. So for this one, we're going to have a struct drm mode map dum mrec, and the mrec, we're going to pass it the handle. Handle is going to equal the handle that was returned to us from the kernel in the first request, so crec.handle. And the rest is going to be 0. They're going to be filled in by the kernel. Okay. Then we will make another IO control system call to do this map dum. And we're going to do the map request. Okay. So this should, if all has gone well, we should have a map request done and a create request done. Now we need to do add frame buffer. So if we look in add FB, this is going to just drive FB2. But we're going to use add FB1. And what add FB1 does is it just sets up the basic format. Add FB2 allows you to specify lots of pixel formats and stuff, and we're just going to choose the basic, straightforward RGB format default for 32-bit wide pixels. And it lets us avoid having to copy in a bunch of more constants from in here. It's an old request that's just kept out of legacy, but it does exactly what we want for our purposes. So add FB. Struct drm mode FB command. FB rec, call it that. We're going to have dot is going to be crec.width. Height is going to be crec.height. Pitch is going to be crec.pitch. BPP is going to be crec.bpp. Depth is going to be 24. Because we're only using RGB out of those 32 pixels. And then .handle is going to be crec.handle, right? The handle that was returned. And it's going to fill in the frame buffer ID. So we can make another IO control call, and this doesn't need to be an int error this time. Okay, well, map dum is going to be add FB, and this is going to be FB rec. Okay, so if all things are correct here, we should have created a dumb frame buffer with the given width and height and pixel depth. It will set up the pitch, which is essentially the the amount of bytes between it won't be a straight 2D array. There might be some space on the sides, which is what the pitch sets up. And then the depth is 24. So out of those 32 pixels, we're only using 24, right? 3 8-byte RGB out of those 24. And we should have a frame, and from the map dumb will allow us to mmap our will get us this offset, which will allow us to memory map the pixels from the frame buffer, and then the add FB request will give us a FB ID that we can use to attach to our CRTC. Okay, so one final thing we need to do is we need to do mmap. So we need to do our U32 pointer mem is going to equal mmap. And let's go to mmap. So start's going to be 0. Len is going to be mrec. What's it called? Map dumb. Oh, it's crec.size. There we are. crec.size. Okay. Protections, we're going to do prot read, prot write. Flags, we're going to do map shared. Not map anonymous, because we're actually mapping from a file descriptor this time. The file descriptor we're going to map from is the card FD. And the offset is going to do that mrec.offset. Map dumb. And that's offset, yeah. Okay, so if mem equals 0, return 0. Okay, if we fail there, we'll return 0. Otherwise, all these things we set up are correct. So we are going to return a dumb buffer struct. And technically, we didn't even need this temp buffer, right? I don't think we even used this arena. Yeah, we didn't even use this arena. So we're good to just go down here. We're going to allocate. So we're going to do struct dumb buffer pointer db is going to equal alloc arena size of db 1. Then we're going to set the dumb buffer equal to all the set of the parameters we need. So we'll say db fb id is going to equal fbrec dot fb id. db height is going to equal crec dot height. db width is going to equal crec dot width. db stride is going to equal crec.pitch, but the since we're treating our memory as a U32 array, this pitch is in bytes, but we want it to be in U32, so we're going to divide by size of U32. I guess we do size of, yeah, we'll do size of db mem back at 0, or dereference db mem, in case we change that to characters or something at some point in the future. For whatever reason, we can just have it be dependent on the type there. And then db size is going to equal crec.size. Okay, and then we can return db. And the only reason we're doing this alloc and return is just so we can return 0 as an indication of failure. There's probably other ways we could have done that, or just panic on failure. But we'll have it fit with all the other requests we've been doing. Okay, so just to be clear, we created a dumb buffer. We got the information necessary to map the memory of the dumb buffer into virtual memory. We created a frame buffer resource corresponding to this dumb buffer. And then we actually mapped the dumb buffer's pixels into virtual memory. We got a chunk of virtual memory that corresponded to the pixels. And we have this width, height, and stride, which is just if we have a row of pixels, the width is how many pixels wide, the height is how many rows, and the stride is how much space there is between the end of this row and the start of the next one in memory. Or sorry, the stride. The pitch is the space in bytes. The stride is the space in U32 32-bit pixels. Okay. So we should be good here. Let's try this. So struct dumb buffer pointer buff db debuff, I'll call it debuff, is going to equal create dumb buffer of card fd let's look at mode. So drm mode info. So this v display and h display are going to be the width and height in pixels of our screen. And so let us choose a mode. So we're just going to choose the first available mode on our connector. So I'm going to do struct drm mode info. Mode is going to equal to con modes. What is it? drm mode get connector. It's going to have a modes pointer bracket 0. So we're just always going to pick the first mode, and then we'll say mode dot, what is it? The width and height are mode dot h display and mode dot v display, and then we'll pass in the arena. Okay. Okay. So we have a CRTC, we have a connector. We're going to choose the mode to be the first mode on our connector. Then we're going to create a dumb buffer according to the width and height of that mode and the card display. So let's try making this. So if I make, what do we have here? 253. Oh, did I accidentally delete something? Oh, I accidentally deleted a semicolon. Add FB. Oh, mode. Okay, so if we make debug this, let's just break on create dumb buffer. Okay, we're going to lay out source, and let's just see how this goes. So let's print width, height. Okay, that looks reasonable. That's close. I have a 19 by 20 by 1080 screen here, and this screen is going to be whatever that is minus some stuff on the top and bottom, right? So that looks reasonable for our height and width. And then let's step through here. So let's print our crec. It has the height and width, bits per pixel 22, and all the other stuff is unset. So if we print here, let's print error. We didn't get an error, and let's print our crec now. So it filled in the handle and it filled in the pitch and the size, the amount of memory required for this dump buffer. Perfect. So our map request is going to have the handle mrec, right? It's going to have the handle, and it's not going to have any padding, and it's not going to have the offset. That's stuff that's going to be filled in by the kernel. So if we print this, we get no error, and if we print the mrec, it gives us an offset into our file. Okay. Now we're going to do our fbrec. Let's print our fbrec to make sure everything looks correct. We have the width and height. That looks correct. The pitch is the same as the pitch. We pre our crec. The pitch is the same as the pitch from our crec. Bits per pixel is 32, depth 24, handle is 1. Handle is the same one that was returned. And the FB ID is not filled in, but if we do make this IO control, let's print error, no error, and if we print our fbrec now, it filled in a frame buffer ID, 40. Okay. Now finally, we can do this memory map request. So we're passing in the offset, the card file descriptor for the map, and let's print mem. It's not null. The map worked. Okay. And if we print our dumb buffer struct, oh, a debuff struct. That's what I called it. So we have a dumb buffer. We have a frame buffer. We have frame buffer ID. We have the width, height, and the stride. The stride is exactly as expected. So there's no extra padding here. And mem is 0. Did I not set the mem in the code here? Create dumb. Yeah, I didn't set the mem. Okay, so we're going to do db mem equals mem. Okay, perfect. Other than that, we're all set. Cool. So the last thing we need to do to draw pixels is we need to attach this frame buffer. So we have this frame buffer ID 40 corresponding to, well, we need to write some pixels in there. We need to attach this frame buffer ID to our CRTC. So to do that, we're going to need to do the set CRTC command. So let's quit out of this, and let's go into here, and let's look at set CRTC. So we're going to have to add this. So it's going to use the same DRM mode CRTC struct, but for set CRTC, we're going to look at we're going to need get CRTC j2, and this is going to be set. Okay. Okay. Get CRTC. Let's implement set CRTC. All right. So set CRTC. Let's look up that DRM mode CRTC. So for the get CRTC, if you remember, we just set the CRTC ID and everything else was filled in. For this new one, we are going to pass in the connector. So in the set of connectors that this is going to be attached to, in our case, it's going to be the same connector that we set up in the first place, that the connector we selected. CRTC ID is going to be set. The frame buffer ID is going to be the ID of the frame buffer we're attaching to this. So it's going to be our new frame buffer. We're X and Y position. You can position this within the frame buffer. We're just going to set it 0, 0. Gamma size, mode valid, and mode. So we're going to pass in a mode and whether the mode is valid. So in our set CRTC, we are going to need to take in we're going to return an error. And what we're going to do is, instead of taking a CRTC ID, what we are going to take is we're going to take a U32 FB ID, a frame buffer ID. We are going to take a connector connector ID, and we are going to take a struct DRM mode info pointer mode. Okay? Okay, we're no longer going to need to do this temporary stuff because we are actually just setting it. So we're going to do struct DRM mode CRTC. CRTC is going to equal dot set connectors pointer is going to equal a reference to our connector ID. Dot count connectors is going to equal 1. We're going to just pass a reference to the one connector ID that we're setting to. The FB ID is going to equal our frame buffer ID. X and Y are going to be 0. Gamma is going to be 0. We're going to set mode valid equal to 1. And then mode is going to equal mode. I guess we'll pass in just the mode. We'll pass it in by value. Okay. Then we're going to do set CRTC with this, and then we're going to pass in a reference to it. And then we're going to return -1 on an error. Otherwise, we're going to return 0. Okay. So let's see. So let's at least see if it doesn't error. So we're going to do int error equals DRM mode set CRTC card FD. And then we're going to pass in. I already forgot what we set CRTC. Okay, then we're passing our frame buffer ID, which is our debuff FB ID. We're going to pass in our connector ID, which, I believe our connector, our connector ID, DRM mode get connector. That has a connector ID value, right? Yeah, it saves the connector ID. And then we need to pass in the mode, right? And that's going to be our mode that we picked out earlier. And we don't need to pass in the arena, which I think maybe we were passing in the arena. So yeah, we don't need the arena. Okay, so can we at least make this? Error is unused, but otherwise we're okay. So just to go over once again, for the set part, we are just setting up this mode and this FB frame buffer ID and the connector that it's attached to. We found a compatible CRTC. Maybe it's connected to the connector or not, but in any case, since we're changing the frame buffer ID, we have to pass in this information anyway. So we're just, if it wasn't connected to this connector already, then we're setting it up. And we're also selecting which mode for that connector is being used, which was what we pulled out earlier here. Okay, so let's make debug. Let's break DRM mode set CRTC. Okay, we got here. So let's print our CRTC request. So it has our connectors pointers, should be correct, one connector. FBID is 40, that's the one we got before, right? Mode valid is 1, and then our mode is the one we selected, right, which looks correct. HDisplay is 1918. VDisplay is 1035. Okay, cool. So if we go next and we print error, we did get an error. Okay. Okay, the issue here is we never set the CRTC ID. So let's go fix that. So we also need to take in a CRTC ID. Set CRTC. So we need to pass a CRTC ID. it needs to know which CRTC we're setting, of course, since we're doing a set, not a get. So let's quit out of here. Let's make debug again. Break DRM mode set. Error is 0. And it filled the screen with black pixels. So, if we should write something other than black in there, what do you think will happen? And I think we should be pretty much there. Okay. So literally all we have to do is that before we set this CRTC is we need to write something into that memory that's not 0. So we're going to go for int y equals 0. I guess we'll just do u32y equals 0. Y less than debuff height y plus plus for u32x equals 0, x less than debuff width x plus plus. And if you remember before, what we're going to do is we're going to set the red equal to the low bits equal to the y, the low bits of the y. So mod 25, the next color, so the green, equal to the x mod 25, and then the last part is x plus y mod 25. So we're going to do debuff mem bracket. This is going to be y times debuff stride plus x. So that's where we get the position. And let's do u32 color is going to equal, we'll do y and oxff, or with x and oxff shift left by 8, and then we'll or with x plus y and with oxff, another layer of parentheses here, and we'll shift left by 16. And then we're going to set this equal to color. So if we make, yeah, we're not using that variable. That's fine. So let's make test and just see what happens. We got a colored pattern. Okay. So all we have to do to animate this colored pattern is run this in a loop. And so what we can do, we drew pixels to the screen. It took an age, but we did it. So all we have to do is run this last part in a loop. So we will do a for we don't need this for loop now. We will have a u32 offset equals 0. And at the end of each loop, we're going to set offset plus equal 1. And we're going to just add offset to each of these. Offset plus y. Offset. Oh no, let me see. What was my animation? I forgot my own animation. What was the formula? Oh, it really should have been. Yeah, that's what it was. Plus x. And then offset plus x plus y. And it's animating. a little jankily because we're not updating on the frame buffer, the frame reset and such. We're not taking frame rate into account, but it's animating. Okay. One last final thing is let's put it on my on my Chromebook. So let's do the process we did before, where we're going to go and we're going to go into this root, right? Remember in our ISO, we find ISO. We just need to replace that that initramfs with the initramfs we just built, right? So if we cp copy dumcycle / initramfs.cpio into ISO / boot / initramfs.cpio. Replace that. Then we just need to remember we need to do grub make rescue. We're going to output to dumcycle.iso. We'll just replace it, and we're taking as input the ISO folder. It worked. And then if we lsblk, we can see that I have my USB drive set in. So all we need to do is dump this ISO there. So we're going to sudo dd in file is going to be dumcycle.iso. Out file is going to be dev sdb, my USB drive, and block size will be 1024K. Okay, it copied. Now let's grab my USB out. Plug this sucker in. And we will boot. Going to our boot menu, select our USB drive. There's a dumcycle. And there's our animating, slowly, but is animating pattern. Okay. It was an adventure, but we got to drawing pixels. And now that we're there, we can make a game next time, and we'll do some interesting stuff with input and evdev. See you in the next one.